Good morning, everybody. Hope you're all healthy and safe. Let us continue with our module 2, and we shall be beginning a new chapter today. It's chapter 7, and in this chapter, we shall be discussing about some function operators and spectral decomposition. So, let us begin. So, today we shall be introducing a definition about what is a particular set. Like we know what is C of AB. C of AB is what? It is a set of all continuous function on the closed interval AB. Similarly, we have capital K of AB. It is actually defined as a set of piecewise continuous bounded functions. Okay, so this is actually not continuous, it is piecewise continuous. Okay, it is continuous in the particular region that we specify. Okay, if AB is divided into particular intervals, or we give a partition, it will be continuous in all the partitions and all. So it is not completely continuous, it is piecewise continuous, and it is bounded also. Okay, now there is one more specialty for such functions, that is these piecewise continuous are actually the monotone decreasing limits of some continuous function. Okay, so K of AB is a set of piecewise continuous bounded function. Okay, they are piecewise continuous and bounded. It is a set of piecewise continuous bounded function having the property that these continuous functions are actually the monotonic decreasing limits of some other continuous function. Okay, so we can always find some continuous function such that that continuous function will be tending to some function in K of AB. I hope the concept is clear. Okay, so we are going to discuss about such continuous functions in today's lecture. So since they are not completely continuous, sometimes they are called as semi-continuous functions also. This is the last point is a notation, that is if you are having any decreasing sequence, say fn, and if it is converging to the function f, then we write it as in this manner. Usually we have the straight arrow, like fn converges to f, but since fn is a decreasing sequence, we put it slightly downward. So we write fn is converging to f. It is a decreasing sequence which is converging to f. Okay, so this is about this is a notation, and we also discussed about what is the elements in the set K of AB. Now we shall do a lemma which will be useful for defining another definition. So the lemma is as follows: let phi of t belong to K of AB. Okay, then there exists a sequence of polynomials Pn of t such that Pn of t is converging to phi of t and Pn is decreasing. I hope the concept is clear. So that is, for any element in K of AB, we can find by the definition of elements in K of AB, we can always find some continuous function which converges to this point, converges to this function. But the lemma is saying that we can always find a sequence of polynomials which converges to the function in K of AB. Okay, so let's see how we can prove this lemma. So first of all, we are going to discuss about a function in K of AB. We are given phi of t in K of AB. So what will be the speciality of this phi of t? Phi of t is an element of K of AB. So this implies phi is continuous, piecewise continuous, and bounded. And one more thing was that it is the limit of some monotone decreasing continuous function, right? This is what is meant by an element in A of AB. So let phi n of t belongs to C of AB, that is a continuous function, such that this phi n of t is converging to phi of t. Okay, because we can find since phi is an element of K, we can always find some decreasing sequence which converges to this phi of continuous function. Okay, so from this is phi n is continuous and decreasing sequence of functions. Okay, now let us consider another continuous function. Consider a continuous function phi n of t plus 3 by 2 raised to n plus 2. This is just for calculation purpose. So let us consider this continuous function. Phi n of t is continuous and 3 by 2 raised to n plus 1, that is also continuous. Then here what we are going to do is we are going to apply Weierstrass theorem. Then by Weierstrass theorem, we have done this theorem, we can always find a sequence of polynomial for every n. Say I'm calling my polynomial sequence to Pn of t, such that this Pn of t will converge to our continuous function, that is phi n of t plus 3 by 2 raised to n plus 2. This is Weierstrass theorem, that is for any continuous function we can find a sequence of polynomials which converges to that continuous function. Okay, so let us write it in mathematical terms. That is, I'm going to write this, that is modulus of Pn of t minus phi n of t plus 3 by 2 raised to n plus 2. It is less than some epsilon, or I am going to take this value to be 1 by 2 raised to n plus 2. So again, this is for calculation purpose only. Okay, so let me just simplify this expression. So what do we get? This implies, by definition of modulus, minus 1 by 2 raised to n plus 2 is less than equal to Pn of t minus phi n of t minus 3 by 2 raised to n plus 2 is less than or equal to 1 by 2 raised to n plus 2. So I'm going to add 3 by 2 raised to n plus 2 on all the sides, so this will get cancelled, and in this side it will be minus 1 by 2 raised to n plus 2 plus 3 by 2 raised to n plus 2. So that is 2 by 2 raised to n plus 2, right? 2 by 2 raised to n plus 2 is less than or equal to Pn of t minus phi n of t, which is further less than or equal to, here if I had plus 3 by, it will become 4 by 2 raised to n plus 2. So again, this is nothing but 1 by 2 raised to n plus 1 is less than or equal to Pn of t, minus phi n of t, it is less than or equal to 1 by 2 raised to n. Okay, now I'm going to consider this is true for every n. So now we get we can get two inequalities, right? 1 by 2 raised to n plus 1 is less than equal to Pn of t minus phi n of t. So from this I can get that phi n of t, if I add phi n of t on both the sides, plus 1 by 2 raised to n plus 1 is less than equal to Pn of t. Okay, so keep this in mind. So let me take this as e. Also what do we get? We get Pn of t minus phi n of t is less than equal to 1 by 2 raised to n. This was the other side of the previous inequality. So this is true for every n. This implies this is for every n. So if I put n plus 1 also, this will be true. Pn plus 1 of t minus phi n plus 1 of t is less than equal to 1 by 2 raised to n plus 1. So this implies p of n plus 1 of t is less than or equal to 1 by 2 raised to n plus 1 plus phi n plus 1 of t. Okay. Now using A and B, I am going to prove that this sequence Pn of t, the sequence is a decreasing sequence. Okay, so let's see how we are going to prove that. And we'll be using the help of the fact that the sequence phi n is decreasing. So we have, just now we saw Pn plus 1 of t is less than equal to phi n plus 1 of t plus 1 by 2 raised to n plus 1. Now since phi n is decreasing, this will be less than phi n of t plus 1 by 2 raised to n plus 1. This was by B, and now by A we get this is less than equal to Pn of t. So I get Pn plus 1 of t is less than equal to Pn of t. So this implies Pn of t is a decreasing sequence of polynomial functions, right? So then Pn of t, we have obtained that Pn of t is a decreasing sequence of polynomial functions, and we had assumed, or we had seen by Weierstrass theorem, that Pn of t is actually converging to phi n of t, right? This is what we had seen. It is converging to the continuous function, and phi n of t is actually, it is converging to a degree. Phi n of t is a decreasing sequence which converges to phi of t. Okay, so we have just now proved that Pn of t is also a decreasing sequence, and using these two implications we get Pn of t is a decreasing sequence which also converges to phi of t. Alright, so this is how we proved the lemma which states that for any function in K of AB, we can always find a sequence of polynomials which converges to that particular function. So that was our lemma 7.01. So with the help of this lemma, we can form this particular definition, that is, let a sequence of polynomials, let us Pn of t be a decreasing sequence which converges to phi of t. Okay, then Pn of a, okay, now we are coming to an operator. Pn of a is greater than or equal to Pn plus 1 of a. That is true because Pn of t itself is a decreasing sequence. So Pn of a is greater than or equal to Pn plus 1 of a, etc. That is also a decreasing sequence, and it will be bounded. Now this is bounded. Why? This is bounded because of the fact that phi of t that we are considering as a limit of Pn of t is also bounded, because phi of t was chosen from, this was an element of K of AB, right? So any element in K of AB is actually set of continuous functions, piecewise continuous functions which are bounded. So phi of t is bounded, and Pn of t, that is a sequence of polynomials, is converging to a bounded function. So that implies that sequence will also have to be bounded. It cannot go unbounded and converge to a bounded function. So if we consider Pn of a, that is function of operator, that sequence will also be decreasing and it will be bounded because of the fact that phi of t is bounded. So here we can apply theorem 6.3.2. so those of you who don't remember the theorem, just go back and refer. By this theorem, for any decreasing bounded sequence, we can find a strong limit. We have proved this theorem. Okay, so the strong limit of the sequence Pn of A will exist, and we call it phi of A. Okay, so this phi of A is an operator that we have defined with the help of the previous lemma. That is, for any element in K of AB, we can find a sequence of polynomials which converges to that point, and with the help of that we can define a new operator which acts as a limit of the sequence Pn of A, and we call it phi of A. So the validity of this definition will be discussed. I mean, how much true it is, that can be seen in the next theorem proposition that we'll be dealing in the next lecture. So just go through the definitions and keep all the definitions in your mind clearly, so that we can move smoothly with the further propositions and lemmas of this chapter. So that's it for today's lecture. Thank you. Stay home, stay safe, stay healthy.